All right, everybody. Good morning. I hope everyone's doing all right. Well done for finding it here. Different location for today. So it's a bit chilly today. Hopefully we'll get warmed up in a bit as we get into the lecture. So as I'm sure you can read, the subject for today, we're going to be thinking about magnetism today. So for the past few lectures, we've been focusing more on electricity and the electric field and charges. And today we're going to develop kind of parallel sort of ideas, but for magnetism. So we're going to see how some of the ideas that we've been developed for electric fields, how are they going to change when we're looking at magnetism? So we're going to start by looking at where magnetism comes from, how we get these magnetic fields arising. But the main focus that we're going to be thinking about is how to deal with the magnetic fields, so the effects they have, how to quantify them, and how they interact. That's the main thing we're going to be focusing on. Now, who has done some magnetism before? Who's done a bit of magnetism before? Okay. So some people on magnetism. Where have people mainly done magnetism before? What kind of courses? A level. Okay. Any other courses? Anyone other than A level? Okay. So there's a few different ways we can kind of approach magnetism as a concept, and today I'm going to do a kind of bit of both, various different ways that we might approach concepts. So we're going to see where magnetism comes from, have a look at a bit of the history, but like I said, the main focus is going to be what's going on with these magnetic fields. That's the plan for today. So to start with a bit of context, do you guys remember way back at the beginning of the semester, we had this Ampere that we were thinking about, where we got the first ideas about static electricity. Do you guys remember this? I know it might seem a while ago now, that in ancient Greece, they noticed there are these very nice rocks, the Ampere, and certain little feathers and things stuck to them, and they called that Elektra. That's where we get the word electricity from. Now, I think there's quite a nice parallel, because there's somewhat of a similar story for where we get the term magnetism from. So ancient civilizations were aware that certain kind of rocks, instead of attracting bits of feathers and stuff like that, attracted other little bits of metal. Now, clearly other ancient societies, they didn't have paper clips. That's a kind of new addition. But, they had other little bits of metal, and they noticed that they would sometimes stick to these stones that they called lodestones. And you can use them to make compasses, very handy. But one of the main places that these special kind of sticky stones were found was in the ancient Greek city of Magnesia. And that might be where we get the term magnet from. Now, these, as we say, they're permanent magnets. So they just sit there being magnetic all the time. Shortly, we're going to have a look at some other kind of magnets where we only get the magnetic field if there's current flowing, so electromagnets. But the story really starts by thinking about permanent magnets. And what I'd like to do is think a bit about where the magnetism actually comes from in a permanent magnet. We just have rocks sitting here, and they're producing these magnetic fields. Where's that magnetism coming from? Does anybody have any thoughts? What, at the kind of lowest level, where does magnetism come from? Anybody have any thoughts about this? What does anybody reckon? So what I'd like to do is take a very sort of bottom-up approach and start from the most fundamental level, where magnetism comes from, and build up the picture until we get to a whole big something like this, like a whole lodestone, which is going to be a whole permanent magnet. So magnetic materials, they really start at the smallest scale with electrons. That's really where the picture starts. And electrons have a fundamental property that we call spin. Now, watch out for this, because in the diagram, it's indicated we've got the little electron and it's spinning, and we call the term spin. They're not really spinning. You can kind of think about it as if they are spinning, if you like. But the point is that it's a fundamental property, and essentially they act like tiny bar magnets. So technically, this property can get very complicated. especially if we get into all the physics behind it. But the takeaway message is, if we think about an electron, we can just think of them as acting like a tiny bar magnet. Of course, they're not tiny bar magnets, but they're just sitting there. They're making those magnetic field lines that you'd get from a bar magnet. Has anybody done, you know, the one where you get the bar magnet and you put the paper down and you get the iron filings and you see where the magnetic field is? Who's done that? Like, have you done that at school or anything? Yeah, it's quite fun, and you can see where the magnetic field goes. Okay, so basically the electrons, they're just kind of behaving like a tiny, tiny version of that. So at the smallest level, this is where we start to get some magnetic field from. Then at the next biggest level, we can get the magnetic field building up in atoms. So if the electrons are all aligned, then those magnetic fields, we're going to get that field building up. And then also, again, this is another kind of diagram where, you know, some physicists, they call it a bit of a cartoon because it gives us some sense of what's going on. But, you know, they've taken a bit of artistic license here because, you know, in the diagram, we've got the little electron here and it's orbiting around the atom. Now, we're going to actually study electron orbitals in more detail in a few weeks' time. And again, this is another one where we can kind of think about it as like a little electron and like a little planet, you know, orbiting the atom. They're not really doing that. We're going to learn all about what's really going on with the atomic orbitals and all that. But again, you can kind of think about this as if we've got an electron and it's spinning around the atom there. Now today we're going to see how current flowing in a loop creates magnetic fields. And this is kind of what we've got here, because we've got an electron and it's moving around and it's spinning around. That's almost a bit like having current going around in a wire, and that's also going to make a magnetic field from us. So we're going to get these magnetic field lines. So we get it from the orbitals, and again, the net result from all of this is that they act like a tiny bar magnet. So this atom, if the electrons are all orbiting around it, it makes a magnetic field, and it's like the atom is behaving like a tiny, tiny atomic-sized bar magnet. So again, to emphasize with both of these, you know, it's not really orbiting, but we can just treat it as if it is a little bar magnet. So that's the kind of atomic scale where we get magnetism from. If we go to the next scale up, we start to get towards a bit of the kind of macroscopic scale. So this picture here is actually a photograph of a crystal from a magnetic material. So the scale here they've put on here, that's 20 micrometers. So it is very, very small, but it's not atomic scale. It's starting to get towards, you know, macroscopic everyday scales. It's the sort of thing you can see through a microscope. And what you can see here is that this magnetic material, it's all divided into crystals, into little regions, which are called magnetic domains. So each one of these little pieces here, you know, one of these has been highlighted, is called a magnetic domain. And within the domain, the idea is that they each behave like a little piece of the magnetic puzzle. So we've got all these domains, and again, each domain acts like a tiny bar magnet. So at every scale, from the very smallest as we get bigger and bigger, each piece of the puzzle is behaving like it's a little bar magnet. So if you imagine in this picture here of the crystal where we have all the domains, imagine putting a little bar magnet in each one of those places, and if they're all aligned in the same direction, that's going to give you a big magnetic field. So you might imagine here, if all of these domains, if they're all pointing in different directions, we're not going to get a net magnetic field. They're not going to combine to give us a magnetic field, give us something that's a permanent magnet. But if we apply a big magnetic field to this region, that can sometimes pull all these domains in the same direction, and then we get a coherent magnetic field. So those are the kind of three big sort of stages where we get the magnetic field building up. Now, I've been talking a lot about, you know, tiny bar magnets. So I think let's have a slide thinking about exactly what's going on with the magnetic field that we get from a bar magnet. And we can also start to think about some of the properties of the magnetic field. So let's take a look over here. So I've got a little picture of a bar magnet. So who had one of these? Like, did you, like, you know, at school, or, you know, maybe had some at home? Did anybody have these? You kind of playing around with them? Yeah. So you kind of know roughly what to kind of expect from the features here. But if we have a look, so we've got the north and south pole, and then we have these magnetic field lines coming out. And again, you can do the experiment, you know, if you have some iron filings and you shake them over, they will trace out where these magnetic field lines go. So the main focus that we're going to be thinking about today for the lecture is the properties of these magnetic field lines. So we've been learning a bit about electric field and the electric field lines. So today we're going to be thinking about the equivalent sort of things for magnetic field lines. So the first thing is that the convention is we say they flow from north to south. So we've got some arrows here, and they have some direction here. So the magnetic fields are flowing in a certain direction. So there's that polarity to it. And every line forms a complete loop. So it might not look like they all form a loop, but they do go around and connect. So we can't just have, like with electric field, you know, lines going out here. With the magnetic field, they always form a loop. And the lines, they can never cross and they can never end. So these are two important properties of the magnetic field lines. And it's important to note that they continue within the magnet. So they don't just stop here and stop at the ends. They keep on going through. So another very important thing about magnetic field lines and magnets is we can never get what physicists, as we say, are magnetic monopoles. Now that sounds a bit technical, but what it really means in English is that we can't have individual north and south poles. Let's have a think now about what the effects that these magnetic field lines are going to have on charges. Now the key thing here is that the magnetic field only affects moving charges. So it's a bit like that scene, you know, in Jurassic Park, and they're trying to escape the T-Rex, and they say, okay, everybody stay still because the T-Rex can only see you when you're moving. Same kind of idea with charges and the magnetic field. So if you just have a charge and it's just sitting there and it's not moving, it's not going to be affected by the magnetic field. But once the charge starts moving, then it's going to be affected by the magnetic field. And the way that it's affected is all in different directions. So there's this quite handy right-hand rule that we can use to get a handle on what's going on with all the different directions. Are you all right? Is it the diagram or just something just totally random? Oh, okay. So I was like, it's not that funny, but yeah, that's fine. Carry on. Okay, here we go. So we got the right-hand rule. So the way the right-hand rule works is that you point your thumb in the direction of motion of the charge. So we've got this here, the V, we got the charge going over here. Now, important technical note is that this V here, this direction, this is the direction of motion of a positive test charge. So remember with the electric field, you know, we're always thinking about positive test charges. So you put your thumb in the direction of a positive test charge. Now what this means is if we're thinking about a negative charge, it's going to be the other direction, because a negative charge, we can essentially think of that as moving in the other direction. So start with, if we're thinking about something with a positive charge, you know, proton, put your thumb in that direction, and then you put your fingers in the direction of the magnetic field. So fingers, they're kind of a bit like magnetic field lines. And then once you've done that, once you've aligned your hand in that way, the force that the particle is going to be experiencing, it's going to be coming out of your palm, which I kind of quite like to remember because, you know, if we're pushing on anything, you know, you push on it with your palm. So, you know, some of these kind of rules are a bit contrived. I quite like this one because, you know, fingers, but like magnetic field lines and the motion, and then you get the force, okay? So we can use the right-hand rule to orient ourselves with the velocity of our particle, the magnetic field, and where the force is coming on. So that's the basic idea with the right-hand rule. The other useful convention that we need to use is because these are all at right angles to each other. If we're just drawing 2D diagrams on a screen or in the textbook or anything, it's quite difficult to kind of get the 3D picture. So we quite often use this convention if we have magnetic field lines coming into or coming out of the screen. So if we have a magnetic field and it's going away from us, going into the screen, we have these crosses. And if the magnetic field's coming out of the screen and coming towards us, then we have these circles with the points on. And I think the idea with these, or at least the way I remember them, is that they're kind of like arrows or darts or something like this, right? So if the darts are coming towards you, they're going to look like this, and this is the pointy end. And if the darts are going away from you, then I guess that's a bit like a dart going away from you. So I mean, that's just how I remember it anyway. So it's quite useful because we've got the velocity and the force and the magnetic field all in different directions. This way we don't have to be drawing nice diagrams in perspective every time. We can have the magnetic field like this, and then we can have the force, and we can have the velocity, and then it's a bit more straightforward to draw. Let's try an example of this and see what's all going on here. So I'm going to leave the right-hand rule here. Suppose we've got a magnetic field. I'm drawing the magnetic field like this. And we've got a proton moving through the magnetic field. So it's got a positive charge. So the question is, if this is the magnetic field and we're thinking about a proton, which of these tracks corresponds to a proton traveling at the fastest speed? So the way to give these questions a go is you want to start by orienting your hand in the direction of the magnetic field. So get your fingers going in whatever direction the magnetic field is. And then try pointing your thumb in the direction of motion of one of the tracks. And then see which way the force is going to be coming from. So which way is the force going to be pushing it, and see which of these tracks it corresponds to. And then remember that the force, it's proportional to the speed. So the fastest proton is going to be experiencing the most force. Okay, let's see what everybody thinks for this one. What do we get over here? Okay, so nobody's going for D. People thinking A, B, or C. Now, these can be a bit tricky, so very well done everybody who gave this one a go. Okay, so let's see how this works. So we got the crosses here. So that means our magnetic field, it's going into the screen, into the wall, like that. So we know what direction our magnetic field is. Now, all the tracks are moving, across the screen this way. So our thumb is pointing in this direction. So the force, it comes out of our palm. So we know that the force is pushing upwards. So we know it's got to be either A or B. Now remember, so the force, it's proportional to the speed. So the faster the proton's going, the more force is going to be pushing it. So the more force it's going to be experiencing, it's going to be pulling it around in a tighter circle. So the correct answer is option A. So very, very well done everybody with that question, okay, because these can be quite tricky. We're thinking about all the different directions. So very well done everybody who gave this question a go, especially if you got option A. Now, please don't worry if you didn't get option A. Personally, I find these kind of questions very kind of difficult with the directions. I'm not even great with which is left and which is right. So, we'll have some more practice with these questions. I'm sure you guys will get the hang of it, okay? So that's the direction of the force acting on a particle. And we have that the force, it's proportional to the speed. So what's useful now is to get a bit more quantitative about exactly how strong the force is. So we kind of know the direction. Let's think a bit more about how strong the force acting on our charge is going to be. So the force depends on the speed of the particle, but But it's not just the speed in any direction, it's the speed in the direction which is perpendicular to the magnetic field. So it's only the component of the speed going across the magnetic field. If it's got a speed in any other part of the direction, that's not going to affect the force. The force it experiences also depends on how strong that magnetic field is, which we call the magnetic flux density, gives it that symbol B. And it also depends on the charge of the particle. So if we double the charge on the particle, it's going to experience a force twice as much. Now, based on these three facts, have a look, which of these relationships, so what's the relationship between the force, the magnetic field, the charge, and the velocity? Which one of these equations describes this relationship? So you don't need to guess with this one. We've got all the pieces of the puzzle that we need. We know the force is directly proportional to the magnetic field, the charge, and the velocity. So have a think about what that relationship is going to look like as an equation. All right, let's take a look. Let's see how everybody is getting on with this one. Okay, nobody going for A or C. Looks like most people going for option D. Now, I can see why you might be tempted by option B, because it is kind of quite sciencey looking. You know, we've got the half V squared business. We've seen equations like that before. But remember, so we've got V squared here. So if we doubled our velocity, then the force is going to be 4 times as big. Whereas what we want is that if we double our velocity, the force is only going to get twice as big. So what we actually want is option D over here. So that's the correct option. So very well done, everybody who gave that question a go. That's the relationship between the magnetic field, the charge, the velocity, and the force. So very well done, everybody, with that question. Has anybody seen an equation or an equation like this before? Okay, now if you've seen this before, you might see it written like this with the V perpendicular, or have you seen it written as just with V and with sine theta? Has anybody seen that? Okay, is that how you saw it? So you might see the equation like this, but if instead it's written with V sine theta, what that means is the V is the magnitude of the velocity, and the theta is the angle between the velocity and the magnetic field. So the V sine theta, it's just giving us the same as this V perpendicular. So if you're not sure about that, you know, we can go over it in the workshop, but it's just the same idea that it's only the component of the velocity which is perpendicular to the magnetic field. So that's what the force acting on our charged particle is. Generally, in kind of day-to-day life, we don't have particles just floating around in empty space. The main situation where we're going to be seeing moving charges is in a current-carrying wire. So a very important example of where we're going to see charges moving around and the effects on the magnetic field. So suppose we've got a wire, it's got a length L. So we know that the force acting on the charges within the wire, it's this BQV, and I've written it as, you know, the V sine theta there, which really means exactly the same thing. Now we know that current is charge per time, and then speed is just length per time, so how long the charges take to move along the length of the wire. So what we can do with this is we can put all these pieces together and we can work out what's the force on a current carrying wire. So we've got a few different options there. I'll give you guys a bit of time to figure this one out. Let's work out what the force is on our current carrying wire. Okay, let's see what everybody thinks. What's the force acting on our current carrying wire? Okay, so some people think it could be D, most people going for B. So really all we need to do is do the substitutions here. So we can substitute that our charge is equal to our current times time, and our velocity, we can just put that in, is L divided by T. So what we get is that the T's cancel out, and what we end up with is just the BIL sine theta. So very well done, everybody, with that question, okay? Now, you might see the force on a wire written as just BIL, without the sine theta. What that means is we're assuming that the wire is perpendicular to the field, okay? So we're just assuming that that angle just gets rid of the sine theta. But to be complete, it's good to think about the sine theta because the force does depend on the angle. So if we have a wire and we put it in a magnetic field, we know that there's going to be a force on it. So it's going to be wanting to be moved around by the magnetic field. But what's really interesting about current flowing through wires is that that current also creates a magnetic field. So as well as being affected by it, it's also making its own magnetic field. And the dynamics of that magnetic field are really interesting, and it's got its own right-hand rule to describe it. So let's take a look at what's going on here, okay? So if we have a wire, we can work out what the magnetic field due to the current is, okay? And we can use a different right-hand rule. So there's two right-hand rules here, so just try not to get them mixed up. So with this one, we put our thumb in the direction of flow of the current. And then same idea, so our fingers still represent the magnetic field, but they don't just go in a straight line, they circle around the wire. So our fingers are kind of, you imagine them circling around, and that's describing where the magnetic field is going. Now, if you're studying physics, when you kind of come to study electromagnetism in full, you can see exactly where we can calculate the strength of the magnetic field comes from and the relationship between the current. But for today, let's just take a look at the result. Let's see what we get here for the strength of the magnetic field. So we get that the strength of the magnetic field, B here, so it depends on the current. So if we double the current, we're going to get twice as much magnetic field. And it's inversely proportional to our distance from the wire. So the further we go from the wire, the strength of the magnetic field is going to decrease. Now this mu naught here, it's another fundamental constant here. So it's called the permeability of free space, quite fancy sounding. It's just equal to 4 pi times 10 to the minus 7 Tesla meters per amp. Now this fundamental constant, it's actually very closely related to that constant we saw, the epsilon naught, the electric constant that we saw a couple of lectures ago. Next week, we're going to see exactly how these two constants are related. But for today, what I'd like to think about, because this might remind you a bit of what we saw when we're studying Gauss's law, we've got this 2 pi r business going on over here. So in this question, let's think about, we've got this 2 pi r popping up in our equation for the strength of the magnetic field. Where's that 2 pi r coming from? Well, let's get a bit of an intuition. Maybe you can recognize what geometric concept corresponds to that 2 pi r over there. So hopefully this one isn't too tricky. If you can recognize exactly what the 2 pi r is, then you can spot it. If you're not sure, have a chat with the people around you. See which of these corresponds to that 2 pi r term in the equation for the strength of the magnetic field. Okay, let's see what everybody thinks for this one. What does the 2 pi r correspond to here? Okay, so some people thinking A, some people thinking C. So it's clearly got to do with a kind of circular region going about the wire. So what that 2 pi r actually gives us is the circumference of a circle. So very well done, everybody who gave that question a go. Okay, that's what the 2 pi r corresponds to. And this is actually described in full by what we call Ampere's law over here. And what that tells us is that if we have some current flowing through a wire, we can relate the current to the strength of the magnetic field by thinking about the circumference, by thinking about the length of a path that surrounds the wire. So if we think about how long is a path going around a wire, well, the shortest path, it's going to be a circle. So that's why that 2 pi r gives us the circumference of a circle. So that's a slightly kind of descriptive way of talking about what's going on with Ampere's law. if you're studying physics, you're going to get exact into all the math you need to figure that out. You've got that to look forward to. So if you're interested in this, take a look at Ampere's law. It goes through the math in a bit more detail. So what we've got is, if we have a wire and there's current flowing through it, it's going to be creating this magnetic field. But then also it's going to be affected by a magnetic field because that current is basically just moving charges. So if we have two wires together, they're both going to be affected by the magnetic field. They're both going to be producing their own magnetic field, and they're both going to be attracted by the magnetic field. So in this question, last question for today, let's think about what the force is between two wires, so two current carrying wires. So just to recap, the first thing we saw, so the force on a wire, it's B times the current times the length of the wire. And there's no sine theta business because we're assuming they're parallel. And then we just saw, so the magnetic field from the wire, it's mu naught times the current times 2 pi r. So have a think about this question. What are we going to get for the force acting between both of these current carrying wires? Now this question might seem a bit tricky with all the mu naughts and the pi's all over the place, but all we're really doing is substituting this magnetic field into this equation for the force, and then we just solve for the force per length. So even though it might seem a bit kind of scary, once you actually work through the algebra, it's not too bad. So give it a go, see what you get for the force per length. All right, let's see what everybody thinks for this one. What's our force between two current carrying wires? What have we got here? Okay, so looks like most people going for option C. So what do we get when we take this B and we substitute in here? We're going to get I1 times I2 and mu naught all over the 2 pi r, and then we solve for the L. So we're going to get option C over here. So very well done, everybody who gave that question a go. That's all we get for the force per length of two current carrying wires. Now you might think, well, that sounds a bit of a niche example. Is it really too important what the force is between two current carrying wires? But this is actually a super important situation because it's what's actually the basis for how we define how strong forces are, and the fundamental basis for the modern definition of a kilogram. So it's actually a really important situation for modern physics and defining our fundamental constant. So this is the force between two wires. And you might just see it solved for the force, but it's often written, in terms of the force per length. So if you have a longer wire, that's going to affect what the force is. So very well done, everybody, with that question, okay? So that's a good place to wrap things up for today, thinking about the magnetic field and the force acting on and coming from some wires. Next time, we're going to build on this, and we're going to see how we can put this together to get super important things like electric motors and electric generators. So super, super important concepts that we get from electricity and magnetism that are really essential for the modern world, okay? So very well done today, everybody. I hope you all have a great weekend, and I'll see you all next week.